Rational computing, general roots. In this video, we'll extend the same principle we used in the last video to calculate square roots to now calculate roots of any degree. Objective: calculate a root of any degree to whatever precision desired, only using integer ratios. What is the simplest way of doing this? An additive sequence can be generated using any number of terms. Here is an example with 3 terms. The next value is constructed as the sum of the previous 3 values. We can construct an additive sequence with any number of terms. 2 terms is related to a quadratic equation, 3 a cubic, 4 a 4th degree, to any degree desired. Just like when calculating square roots, we can use the coefficients of an equation to modulate our additive sequence. Let's look at an example. X cubed minus 2x squared minus x minus 4. This generates the sequence 0, 1, 2, 5, 16, 45, 126. Observations. The ratio of 2 adjacent terms of an additive sequence that is modulated by the coefficients of a polynomial approximates a root of that function. The more iterations, the better accuracy. This works for polynomials of any degree, but only certain polynomials. We can rebase the polynomial into a form that does work. Prerequisite: data phase. In my video series Data and Math, I introduced the concept of rebasing a polynomial. Essentially, this allows us to move the coefficients of that polynomial along a derivative and derivative-like relationship to generate a new polynomial whose roots are different in a known way from the original. We can then perform our calculations on the valid polynomial and adjust our answer based on the known relationship of the roots. Algorithm. Start with x to the degree minus the target desired. Rebase the polynomial. Solve with an additive sequence. Correct the result for the rebasing. Let's work out an example. The 5th root of 17 as a polynomial. X to the 5th minus 17. Rebase -1. X to the 5th minus 5 x to the 4th plus 10 x to the 3rd minus 10 x squared plus 5x minus 18. Modulated additive sequence as a decimal value. I've implemented this algorithm at math.d8data.io under the General Roots app. It compares the result with the conventional standard library results. We can adjust the root and the degree and the iteration count, and compare the results to the conventional calculations.